In this session, we discuss the use of Gaussian PDF and the introduction of new function called Q function. As we discussed in last video lecture, Gaussian CDF cannot be evaluated as the result of integration is not a finite value. So, there is a requirement of introducing new function called Q function, which is basically used to evaluate the effect of noise in digital communication. This Q function can be easily evaluated and give a finite result. To represent Q function, we use a Gaussian PDF with mean value 0 and variance sigma square equals to 1, that is shown in figure. And the expression of Gaussian PDF is small f function x equals to 1 upon under root 2 pi e to power minus x square by 2. On this Gaussian PDF curve, we introduce a Q function. So, Q function is represented as the area of positive tail. Here the probability of observing x greater or equals to y is given by the shaded area called a Q function or capital Q function y. As the probability of observing random variable x at 0 mean value is maximum and this value decreases below and above mean value. So at the tailing edge, the probability of observing values is very small. So at the positive tail of Gaussian PDF, we introduce a Q function that is equal to the area under the curve, that is shown by shaded region. And this Q function is widely used to evaluate the effect of noise in digital communication. Now, in order to determine probability of observing x greater or equals to y, we have to compute the shaded area. To find shaded area, we have to integrate Gaussian PDF function with respect to dx and taking limits from x equals to y to x equals to infinity. Now, in place of small f function that is called Gaussian PDF, we can write expression with 0 mean and unit variance, and it is equals to 1 upon under root of 2 pi into e to power minus x square by 2 into dx. So this integration expression is called Q function denoted by Q function y, and this results as area of shaded region of the positive tail. After discussing the significance of Q function for noise performance in digital communication, we set a relationship between PDF, CDF and Q function. Again, the Gaussian PDF with 0 mean and unit variance is given by a function that is small f equals to 1 upon under root 2 pi e to power minus x square by 2. So, using Gaussian PDF, Gaussian CDF is evaluated, that is capital F function x equals to 1 upon under root 2 pi integration e to power minus x square by 2 into dx. Here we take a limit from minus infinity to x. But this integration cannot be evaluated as we get no finite result, that is shown in figure. For this observation, we can introduce a new function that is called Q function. This Q function can be easily computed and get a numerical value. So the Gaussian CDF can be evaluated in terms of Q function, which is equals to the area under the positive tail of Gaussian PDF. Now, according to the property of Gaussian PDF, the total area under the Gaussian PDF curve is unity. So the remaining area other than Q function is denoted by Q function of minus y, and it is simply equals to 1 minus Q function y. So on the basis of these observations, the Q function is represented at the positive tail region shown by shaded area, and it is equals to Q function y, and the remaining area is called Q function of minus y. And Q function of minus y is simply equals to 1 minus Q function y. Now, for the expression of Q function, we first find the area of shaded region. and it is equals to integration of fx dx, taking limit x equals to y to plus infinity, and in place of fx, that is called Gaussian PDF, we can write 1 upon under root of 2 pi into e to power minus x square by 2, and this integration expression is called Q function y, which shows the area of shaded region where we have minimum probability of observing random variable x, and there is a maximum possibility of occurrence of an error. Now, as we see in expression of Q function, limits are from x equals to y to plus infinity. So the evaluation of this integration is possible as it gives a finite result. Also, we note a point. This Q function can also be used to determine Gaussian CDF. So Gaussian CDF, that is capital F function x equals to 1 minus Q function x.